Hello, good people. Welcome to the last section in Unit 4. There is just something I want to point out. The official, I guess, the Passwater title here is L'Hospital's Theorem and Indeterminate Forms. I do want to point out that a lot of times, a lot of professors and textbooks call this, or I guess write this, L'Hôpital's. Some even put a little symbol there above the O. I don't know what it's called, but it's a French name, so it's L'Hôpital. And sometimes they don't call it a theorem; they call it a rule, L'Hôpital's rule. And there's like a history and a very interesting story behind L'Hôpital's rule, which is how I pronounce it. Some people pronounce it La Hospital's rule or La Hospital's theorem, as is written on the paper. But it's going to be a tool to help us find limits. Limits, which were part of Unit 1, limits, which was part of the creation of the derivative, but we're going to actually use derivatives to help us find limits. And that's what L'Hopital's rule is all about. In a subsequent video, I'm going to give you an option to watch the explanation behind L'Hopital's rule and why it works. But for right now, we're just going to accept that it is a theorem that works and we're going to use it as such. Anyway, so as we start, let's remember from Unit 1 that whenever we're taking a limit, the very first thing you should try to do is direct substitution. So I'm looking at this limit. I'm going to try to do direct substitution. Remember that whenever you are taking the limit and it's a ratio, it's a fraction setup, always take the limit of the top separate from the limit of the bottom. So I'm going to take the limit of the top and we're going to get an answer. We're going to take the limit of the bottom and we're going to get an answer. Now, if I substitute 4 into the denominator, 4 squared is 16. 16 minus 16, that would be 0. If I plug 4 into the numerator, 4 squared is 16, plus 2 times 4, that's 8. So 16 plus 8, that's 24. Minus 24, that's also 0. So this actually produces what we called an indeterminate form. And so this leads us to an indeterminate form. Now, the reason it's called an indeterminate form, we talked about, is because I can't determine what's going on. And the reason I can't determine what's going on is because when I have a fraction, if the numerator starts to get smaller and smaller and smaller and closer to 0, the whole fraction, or the fraction as a whole, I guess, the value of the fraction gets smaller and smaller and smaller and smaller. However, if my denominator, whatever I'm dividing by, gets smaller and smaller and smaller, closer to 0, the whole fraction starts to grow, right? Like if I take, let's say I take 10 divided by 0.1, I'm going to get 100. If I take 10 divided by 0.01, I'm going to get 1,000. 10 divided by, you get the picture. The idea is as my denominator goes smaller towards 0, my fraction gets bigger. So there's like a fight going on between the numerator that wants to go to 0 and make the whole fraction smaller, and the denominator that wants to go to 0 and make the whole fraction bigger. And so we can't determine what's going on. I do want to point out there's another form of indeterminate setups. One of them is 0, 0. That's the one that we noticed happened in Unit 1. There's also infinity over infinity. That is also an indeterminate form. I can't determine what's going on because if the number gets bigger in the numerator, the whole fraction starts to get bigger. But if the number in the denominator gets bigger, well, then the whole fraction gets smaller. So there's a fight going on. There's other types of indeterminate forms, and in a calculus class in college, you would probably, maybe an advanced calculus class, you would study the other different types of indeterminates. All these 4, we don't really know what's going on because there's a contradictory behavior, right? I'm multiplying by 0, so that's trying to make things disappear and go to 0. But I'm multiplying times infinity when infinity is like a big number. So there's that fight going on. The 4 that I circled in green are not going to appear on the AP exam. The only indeterminate forms you will see on the AP exam are 0 over 0 and infinity over infinity. So we know this is an indeterminate form. Back in Unit 1, we said algebraically, we can figure this out, right? If we factor the numerator, factor the denominator, oh, look, this is going to reduce, and I'm left with the limit as x approaches 4 of x plus 6 over x plus 4. And then I can try to evaluate the limit again by plugging in a value of 4 wherever I see an x, and that's how we got our answer. So there is an answer, right? I guess indeterminate forms don't mean that the limit doesn't exist. It just means that I can't tell what the limit is by doing direct substitution. There has to be something else I can do. And that's what we try to do. The problem with that is we can get something that looks like this. Now, if I do direct substitution of the numerator, e to the 2 times 0, well, 2 times 0 is 0. E to the 0 is 1, plus 0 minus 1, that gives me to 0. And if I do the same thing in the denominator, well, I get 0 as well. So I took the limit of the top, took the limit of the bottom, and I get an indeterminate form, 0 over 0. However, in this case, there is no way to factor and reduce because this is not a polynomial function that can be factored. This is an exponential with the polynomial function. It's like a mixed function. So what do we do? And so L'Hopital's theorem or L'Hopital's rule is here to help us in situations where we can't do what we did before. And I will admit that some students say, well, even if I know how to do it this way with the factor and reduce, L'Hopital's rule actually speeds up my work. But I couldn't do it before because I needed the derivative as a way to apply L'Hopital's rule. And so here's what L'Hopital's rule says. It disappeared. L'Hopital's rule says, if you have two functions, they have to be differentiable, meaning I have to be able to take the derivative on an interval from a to b. And inside a to b, there's an x value called c. So as long as it's differentiable on all values between a and b, possibly at c, possibly not, and as long as the derivative of the bottom part is not equal to 0 for all x's, except maybe at c itself, then here's what we know. So there's some that we already have some conditions, right? I have to have two functions. They have to be differentiable on an open interval. We have to assume that the derivative is not equal to 0 for all x's except maybe at the x value c itself. But here's the biggie. And the derivative, and the limit as f of x as x approaches c is 0, and the limit of g of x as x approaches c is also 0. What that means is when I try to substitute c in, the limit of the top is 0 and the limit of the bottom is 0. This would also work if the limit was infinity and this was infinity. If we have this going on, if we get an indeterminate form, L'Hopital's theorem, L'Hopital's rule says the limit of the original setup is equal to the limit of the derivative of the top over the derivative of the bottom. Notice, this is not the quotient rule. It is not saying do the quotient rule to verify. It's just saying if you get an indeterminate form for a limit that looks like a ratio where you're dividing top divided by bottom, then take the limit again, but this time take the limit of the derivative of the top over the derivative of the bottom, do direct substitution and see if you can get an answer, because if you do get an answer, that is the limit value. So let me go back. Would that work with the example that we had originally? So here was our example. Did it meet the conditions? Is x squared plus 2x minus 24 differentiable? Can I find the derivative at any x value? Sure. X squared minus 16, is that differentiable? Can I find the derivative of x squared minus 16 at any x value? Sure. Did I take the limit of the top and did I take the limit of the bottom and did I get a 0 on both? Yes. So according to L'Hopital's rule, I can take the limit as x approaches 4 of the derivative of the top, which is 2x plus 2, over the derivative of the bottom, which is 2x, and try the limit again. Do direct substitution again. So that would be 2 times 4 plus 2, and this would be 2 times 4. Well, this would be 8 plus 2, that's 10, and this would be 8. And if you reduce that, I believe that's 5/4. And that's exactly what we got over here when we did the factor and reduce. Was it shorter? Yes. Was it faster? Yes. Did I have to know how to take the derivative? Most definitely. And that was not something we knew how to do back in Unit 1. So now, from here on out, if you get an indeterminate form that's 0 over 0 or infinity over infinity, use L'Hopital's rule as the shortcut to get us to that. Now, before we do some examples, Brian does point some things out. This is a theorem, right? It has conditions. If the conditions aren't met, then I cannot apply L'Hopital's rule. So I got to make sure, do I have differentiable functions on an open interval containing the x value that I'm approaching, if that's true, and if the limit of the top is equal to 0 and the limit of the bottom is equal to 0, or is the limit of the top infinity and the limit of the bottom infinity, then I can approach this limit with L'Hopital's rule. Also, remember that these are indeterminate forms, they're not numbers, so don't say a limit is equal to infinity to infinity, because it's not true. It doesn't equal that. It is just what we get out of it, right? And so be very, very careful. Don't write it that way. If you are going to work with a limit problem where you have a top and a bottom, take the limit of the top, he says, take the limit of the bottom. If both the tops and bottom is 0, or both the top and the bottom are infinity, then we can apply L'Hopital's rule. After you find L'Hopital's rule, or after you apply L'Hopital's rule, then you can find the limit of the numerator and the denominator again with a derivative. And then if that doesn't create an indeterminate form, then whatever we get there, that is the answer, right? And so that's exactly what example 1 was. I believe that was just the one we just did. And then we can look at example 2, which now we're able to do by just taking the derivative. But can I apply L'Hopital's rule? Well, I don't know. We got to check. If I take the limit as x approaches 0 of e to the 2x plus x minus 1, oh yeah, we do get 0. Oh, wait a minute. This is the one from the other side of the page. This looks familiar. Yes, we get 0 on top, 0 on the bottom. So we can do L'Hopital's rule. So here we go. We're going to take the limit as x approaches 0. That doesn't change. And then I'm going to find the derivative of the top. Don't do the quotient rule. L'Hopital's rule just says take the derivative of the top, take the derivative of the bottom, try the limit again. The derivative of e to the 2x is e to the 2x times 2 plus the derivative of x is 1 minus the derivative of 1, that would be 0. Okay, go to the bottom. The derivative of x squared is 2x. The derivative of 4x is 4. And now let's substitute the 0. So I'm going to take the limit as x approaches 0 of the top. If I substitute 0, that's 2 times 0 is 0. E to the 0 is 1 times 2 is 2 plus 1, that's 3. And then I'm going to take the limit as x approaches 0 of 2x plus 4. If I substitute 0, I'm going to get 2 times 0 is 0 plus 4, that's 4. So therefore, my answer is 3/4. And that is the answer. That is the limit of this function. In the next video, we'll do some more practice with L'Hopital's rule. But again, the idea is if we have indeterminate results from doing direct substitution on a limit, then we can apply L'Hopital's rule as a shortcut to finding the answer.